Fisheries worldwide are typically managed through a single species approach that focuses on one species at a time. Fishery scientists and the fishing industry are investigating the potential benefits of applying a multi-species management approach to groundfish fisheries in British Columbia, Canada. Single species management usually aims to maximize the long-term yield of each individual species. It ignores the interactions that occur between fishing gear and fish species that are caught together. For the British Columbia groundfish fishery, those interactions can be directly considered by using catch and effort data from each of the fishing sectors, which differ by how and where they fish. Instead of aiming to maximize fishery yield for a single species, this research is focused on maximizing long-term economic benefits over many species. The approach shifts perspective from short-term decision-making, aimed at maximizing yield for individual species, to a broader system view that supports long-term sustainable use of many species. By doing so, management measures could be identified that avoid unacceptable risks to fish stocks in British Columbia and the fisheries that depend on them. Let's begin by understanding single-species management. Most fishery goals originate from the concept of maximum sustainable yield, or MSY. Here's how it works. Fishery scientists think about the maximum level of catch, or yield, that could be maintained over a very long time without depleting a fish population. This theoretical yield is called MSY. It occurs at the fish population size or biomass that is most productive, called BMSY. When population biomass is above BMSY, productivity is lower and long-term yield will be less than MSY because the population is underfished. When fish biomass is below BMSY, productivity is also lower, and the long-term yield is also less than MSY because the population is overfished. Managing fisheries to an MSY objective does not mean taking the same maximum yield every year. We need to account for unpredictable variation in the environment that also affects fish production. Therefore, catches must be adjusted, sometimes frequently, to ensure a sustainable fish population. In addition, the MSY concept only considers yield and not the fishing costs required to go out and catch it. In general, fishing costs like fuel, bait, and crew wages depend on the size of the fish population. Harvesters know that fishing costs increase with the amount of effort expended to catch fish. Their goal is to attain the maximum catch for the lowest cost. Therefore, it is not necessarily about the size of the catch, but instead about the revenue minus the cost of attaining that catch, or resource rent. Fishing costs are higher when a species is overfished because it takes more effort to find and catch those fish. This means resource rent shrinks. The opposite occurs for underfished species. The fish are easier to find and more fish are caught for each haul of the gear. More fish per haul spreads the fishing costs over more fish and therefore increases resource rent. The one drawback to underfishing is a loss of potential yield compared to MSY, which means a lower overall level of rent. This drawback leads to an alternative definition of optimal yield that instead maximizes resource rent. In other words, the most revenue at the least cost. The most profitable catch level is called the maximum economic yield, or MEY for short. MEY is generally smaller than MSY, but taking slightly less catch leaves more fish biomass in the water. This lowers costs of fishing and results in a higher resource rent. Maximizing economic yield is, therefore, a reasonable alternative to MSY, especially for multi-species fisheries, where simultaneously achieving MSY for several species is nearly impossible anyway. Single-species management, using goals related to either MSY or MEY, works perfectly well if there is just one species in the ecosystem, or where a fishery can selectively catch just one species at a time. In the British Columbia groundfish fishery, many species are caught together, so an MSY approach creates the risk of over or under harvesting several species, even the most economically valuable ones. A more deliberate multi-species approach considers how fish species are caught together when making management decisions, rather than reacting to the status of each species independently. Why haven't we already adopted multi-species management? Although management of fisheries have been built on the single species MSY approach for decades, fishery scientists and managers just don't have a pragmatic foundation to implement a multi species approach. In fact, diversity in species productivity means that each individual species has a unique MSY, so we cannot, even in principle, optimize harvest for every individual fish species at once. Individual species in a multi species fishery would be over and under harvested when managing to MSY. This research is asking two key questions. Would the British Columbia groundfish fishery benefit from adopting a multi species management approach? And would managing to multi species MEY produce better outcomes for species and fisheries than management to MSY? The research is built on historical fishery data, fish stock assessments, management plans, and seafood economic supply and demand relationships. Multi-species analogs to single-species MSY and MEY calculations will be developed, leading to a focus on the aggregate yield for a mix of species. The analysis originates from the concept of technical interactions that describes how multiple species are caught by the same fishing gear. Knowing how fishing gear interacts with target and non-target species over space and time can inform harvest strategies based on either MSY or MEY. Over time, some species in the mix may be underfished, and some may be overfished. But the aim is to ensure no single species declines to levels of abundance that pose unacceptable conservation risks. And managing to MEY may mean higher fish biomass can be maintained as well as higher profits compared to managing to MSY. New computer simulation modeling will help develop a better understanding of the economic and conservation risks of single-species management and shine a light on the potential advantages of multi-species management based on the technical interactions of fishing gear with fish populations. Those simulations will help to understand the way fish populations might respond to assumptions about current and future abundances of species in the fishery, the mix of gear types that catch the fish, and the management actions applied as the mix of species change in abundance over time. The computer simulations are used to evaluate management options based on MSY or MEY harvest strategies. The advantage of computer testing is that options that perform poorly in a simulated fishery can be eliminated without risking the actual fish populations and fisheries. The best performing options can be considered for application. A multi-species perspective based on MEY may provide a better approach to managing risk compared to the single-species approach, since most species would be fished less intensively in order to maximize total resource rent. In this way, multi-species management could be a practical gateway to sustainability that benefits fish stocks, fish harvesters, and dependent fishing communities. Fishery managers would also benefit from a multi-species approach because higher species biomasses and less intensive, more profitable fisheries would lower overfishing risks and the need for expensive and time-consuming rebuilding plans if things go wrong. Improving management for groundfish fisheries in British Columbia will help meet eco-certification requirements. This, in turn, helps to maintain access to global seafood markets. Multi-species management is not only a potential benefit, it's becoming a necessity to meet public expectations and the needs of today's fishing community.